Welcome back. In this lesson, I want to make an extension of the 1D radial basis interpolation out to n-dimensional. So once again, starting off with theory. So the theory is very much similar. We have a radial basis function, and then we define the interpolation based on basically the Euclidean distance of every single point from each other point, x of k, that we have in our interpolation function into the radial basis function and then multiplied by a weight. So the difference on this is on this definition here, you can see we have, these are now bold. So this represents that these are vectors. So as in priorly, we just had one data point. We now have a vector. So it could be, each one could be 2 data points, or it could be up to n data points, depending on what dimension we have. So let's see how we can implement something like this and using just Python and numpy. So again, we have our imports numpy and matplotlib, and then this right here is the radial basis interpolation class that we created in the last video, except on here I did make a few minor modifications. So I decided to implement the Gaussian radial basis function inside of this class since we're using the epsilon, and so I thought that was just easier, just so we can encapsulate that we already had the epsilon inside the class. But besides that, it's pretty much the same. On the last video, I did make a minor mistake. This is supposed to be self.x of k underbar. So if you're watching on the last video and were wondering, that was corrected. So as we did with last time, let's sort of make a toy data set so we can kind of get going with this concept. So I'm going to make a function that generates some toy data set. Generate data. And so let's see here. We give it numpy.linspace. So we're gonna make this a 2D data so that we can visualize it, so it's easier for us to comprehend like what's going on. So x1 equal to numpy.linspace of 0 to 1, and we'll give it 10 data points. Let's do x2, same thing. And then now we're going to make a mesh grid. So xx and xy equal to numpy dot mesh grid, and we'll give it an x1 and x2 so that we have a grid that we can plot the function on. And before I do this, actually, let's make another function that is going to be the surface of this grid that we're generating. So let's give it a function, and it's going to get an x1 and an x2, and we're going to just return, let's say it's x1 squared times numpy.cosine of 2 times pi times x2. And so we'll say y is equal to our function. We'll give it xx, xy, and then let's return all this. Now I'm going to return this sort of in a way that is typical in most sort of data science project, where each row is going to be an observation and each column is going to be a variable. So how I want to do this is I want to concatenate these xx and xy. So we're going to say numpy.concatenate xx, and then since these are going to be basically 10 by 10 right here, I want to make those just a vector. So reshape it to be just one column. So column vectors. So xy.reshape minus 1 by 1, and then I want to concatenate these along the first y-axis. Axis is equal to 1. That way, hopefully, whenever this should return us back a basically a 100 by 2 vector or matrix. So we're going to return that, and then we're going to return y, and then again with the y, I want to reshape it to be just a column vector. So let's see here. We should get our data and our y test. is equal to generate data set. Let's see, data. So let's see, it looks like it is the correct shape, 100 by 2, and y test is 100 by 1, so that looks correct. Now, so what we want to do now is let's kind of actually see what this function sort of looks like and visualize it. So again, I'm going to make another little helper function here called plot function, plot the real function. So we're going to give it a function, and then we'll give it a resolution. I'm going to give it a default resolution of 100. So it's going to be 100 data points, 100 by 100 grid essentially. So what we want to do here is, again, we want to do x1, and there's going to be a lot of reuse here, so I'm just going to go and let's just reuse some of this here that we did before, except of going to the default to 10, we're going to use resolution. Resolution, xx, xy, okay. Now let's go ahead and plot a contour of this. So we're going to use the contour, plt.contour, xx, xy, and then we're going to give it y. Sorry about that, I made a minor mistake on the spelling here. So let's see, cs is equal to ps.contour, and then let's go and label it. So plt.cLabel, and we'll give it our contour line. So if we do this, this should hopefully plot out the real function of our function. Pass that in, and then as you can see, we get a small little contour. And then if you want to, we can go ahead and also plot out our plt.scatter. We can show the grid along here as well of where we're have our data points. So I'll have data at 0, and then our data on column 1. This should hopefully make a grid. And let's make this a little bit bigger so you can see it a bit better. plt.figure fig size is equal to 12 by 8. So there you go. So now you can see this is sort of our test data. So we have a function that sort of has like, looks like, you know, sort of 3 little maximums around 1 or so, you know, right here, right here, right here. And then it just kind of goes off into nothing out here. So let's see if we can make an interpolation that can, using these blue data points here, basically approximate what this curve looks like. So the first thing that you can see here on this class that we created is that we need to go and redefine what this Euclidean distance is. So as you remember on the last video, we determined what the Euclidean distance was in 1D, but we need to do a few more different steps in numpy to do this in 2D. So to kind of illustrate this, first I'm gonna kind of make a small test data set that we know what the answer should be. So let's say test data is going to be equal to numpy.array. I'm just going to make it a 3 by 2 array. So it's going to have 3 data points, 0, 0, 0.5, 0.5, and then 1 by 1. And then we'll reshape this to be a 3 by 2. So we have our test data. So here's our test data here. So as you can see, we have 3 points, 0, 0, 0.5, and 1, 1. And so what we want to do is we want to compute what the distance is from this point, and this point, and then again do it for this point, and this point, and then again this point, from this point, and this point. And so what we should get whenever we compute the Euclidean distance is essentially a 3 by 3 matrix. So let's see how we can do this. So the first thing we want to do is we want to break this back down in sort of the one-dimensional problem that we had before. So what I'm going to do here is I'm going to give this test data a new axis, ... So here we go. So now it's wrapped in another one. And so what I want to make this is I want to make this into 2 column vectors. So then I'm going to swap axes. So this right here is a 1 by 3 by 2, and I want this to be a 2 by 1, no, 2 by 2 by 3 by 1. So we want to swap axes 0 and 1, 0 and 2, and there we go. We have 2 column vectors. So this will be kind of our first one. So we'll say test call. And now, as you remember from the last episode, we had to do make it a row vector as well. So, following the same extension, we'll go and make a row vector. So the first thing I want to do is I want to take the test data and I want to transpose it. So now we have basically 2 row vectors. And then again, we can do the same thing we did in here. numpy dot new axes dot dot dot. Let's see, so the shape of this is a 1 by 2 by 3. And so again, we want the first axis to be 2, and we want to have a 1 by 3, because this one right here is a, this right here is a 2 by 3 by 1, so this one needs to be a 2 by 1 by 3 for whenever we broadcast it. So we want to, again, swap the axes 0, and we want to swap axes 0 and 1. Swap axes 0 and 1. So dot shape. So we have a 2 by 1 by 3. So now these should broadcast, and they should give us sort of the difference of each point from each other whenever we subtract the 2. So let's see if we can test that. So let's see here. So this is going to be test call equals this, and test row is equal to this. So now if we do test column minus test row, we should broadcast it correctly. And as we can see, we did. And so sort of looking at this, it's kind of like what we expect. So the first point from itself is 0, the last point from itself is 0, and the other two, the middle point from itself is 0. And then as you can see, 0 minus 1, which is the last point, is minus 1, and 0 minus 0.5 is minus 5. So it looks like we got this correct. So what we want to do for the Euclidean distance now is we need to first square these, every single term by each other, to get rid of the negative signs. So now we've gotten rid of the negative signs, so you can see everything is a positive. And then we need to sum it now back. So now we have 2 3 by 3 matrices. We need to reduce that down into a single 3 by 3 matrix. So we can go and create the sum. We want to sum it over that first 0th axis. Axis is equal to 0. And there we go. We now have a 3 by 3 matrix. Now the only thing we have left to do is, since we squared it, is we need to take the square root of it. So we take the square root of it, and this appears to be about right. So you can see, we have zeros along this, meaning each point from itself is that, and then it's increasing as it goes further away. So that looks like this is going to work. So now that we kind of have an idea of what we need to do, we can now implement this Euclidean distance function so that this class will function correctly. So let's go ahead and define our Euclidean distance. Euclidean distance. And so we're going to, again, like last time, we're going again to give it an x and an x of k. And so here we'll just go and just kind of do exactly the steps that we just did before. So we'll say x is equal to x, numpy to new axis, the ellipses operator, and then we want to swap axes 0 and 2. Then x of k, we're going to do the same thing, xk transpose, and then we're going to do numpy dot new axis, the ellipses operator, and then swap the axes 0, and 1. And then now we can return the result. So we'll say x minus xk squared, and we want to sum this over axes equals 0, and then we want to take the square root of it. T. And now let's test it with the data we did before and see if we can get the same result. So we'll give it our test data with itself. And as you can see, it looks like we got the same result, so it looks like this function is probably going to work for what we're doing. So now that we've implemented this function, this class should work. So let's see if we can now approximate this sort of toy data set that we had before. So we're going to have our model, our interpolator will be equal to radial basis function interpolation, and let's give it a gamma of 3. And now let's see if we can fit it to our test data, or not our test data, but these data points that we defined here before, which is our data and y test. So we're going to interp, and we're going to fit it to our data and y test. And I misspelled, so let me fix that. I need an N. And so now we have our fitted data, so we should have a W term. And let's check it's the correct shape. Yep, it's 100 by 1. And we have our x of k, and it looks like it's the correct shape as well. So now let's see if we can compare our fitted model to the actual function. So again, I'm going to go and sort of copy all this here, so we can reuse most of this here, but we need to make a few minor modifications. So let me see if I can copy this down here. And so instead of plotting real function, we're going to say plot the interpolation. We'll give the same resolution, and we'll pass it the interpolation function. So these right here will be the same, except now, since the way we have our interpolation function, we need to just pass it our data set. Oops. So let's see if we can do numpy. We'll make our data equal to numpy dot concatenate. We'll do xx, again reshape it to be reshape minus 1 by 1, and xy dot reshape minus 1 by 1, and again axes equals 1. And then we can pass that to our function. Except change in word, this should be our data. Oops. Our data. And then it should give us our output. So here, so there we'll have xx, xy, and then instead of here, what we need to do here is we need to reshape this to be our resolution by resolution. To make sure this function works correctly. And that should hopefully plot it. So let's see if this will work. Plot the interpolation, and we want to give it our terp. And let's see what this does. So as you can see, it plotted our interpolation, and looking back to what we had before, we can see it's pretty close to kind of what we had before. So hopefully you found this video useful. If you like the material and want to see more, leave a like, a comment, and if you really enjoy it, consider subscribing. Thank you. Bye.